So I want to make some clarifications today about when I say the dot product is multiplication. The reason I want to bring this up is because I always say that the dot product is multiplication at an angle. So sometimes I'll say the dot product is multiplication at an angle. Or similarly, dot product is multiplication when direction gets involved. So the dot product is multiplication at an angle or multiplication with direction. So the part where we have direction involved means we can't just consider magnitude. So dot product with direction means we can't just consider magnitude. The reason I want to make this clarification is because I'm going to be saying this a lot more, and I want to make sure it lands. When we think about, I want to think about the dot product as multiplication with direction involved. The reason for this is that multiplication is our basis for integration. Multiplication and addition form our basis for integration. When we the first operation that we learn when we learn how to name amounts and name quantities, the first operation we learn is addition. It's the very first math thing that we learn. Once we learn the words and how to name quantities, we learn addition. Once we learn addition and its companion subtraction, we learn about multiplication. Multiplication is what we do when all the things are the same. When all the terms are the same, we get to use multiplication. We just count up the number of terms and we get to use multiplication. Fast forward quite a bit. Fast forward to calculus when we start doing integration. And integration is based on the same idea. Integration is multiplication, but one of your factors is continuously variable. We deal with the variable part by doing the same thing that we always do. We have to just drop back to addition. We get to use multiplication if all the terms are the same. If all the terms are not the same, we don't get to use addition or don't get to use multiplication. We drop back to addition. Classic math solution to problems. Do the other problem. Do an easier problem that you already know how to do. The other thing that we come across in integration is that one of the factors is continuously variable, not just variable, but continuously variable. So our solution of dropping back to addition poses another problem because in a continuum, there's nowhere to put the plus sign. In a continuum, there's nowhere to put the plus sign. In a discrete sum, there's the plus sign is what separates all the terms. But in a continuum, there's nowhere to put the plus sign. So we improvise. We do the same thing that we always do. We do a problem that we know how to do. Instead of having things be continuously variable, we have them be constant on little chunks. That way we get to put a plus sign somewhere. Then we just use more plus signs and more plus signs. And then we cross that boundary. We think about what would happen if there's just infinitely many plus signs. If everything is smooth. When we go from a discrete sum that we're using to approximate our continuum to a continuum. We think about what would happen there. So with that in mind, dot product is a form of multiplication. So dot product is going to show up in integrals at some point because it's multiplication. That's what integration is for. Integration is for multiplication, where one of the factors is continuously variable. One way we can multiply is with the dot product. So let's clarify some things about dot product. If we have no direction, for a bunch of young college students, that may hit close to home, phrasing it that way. But anyway, if we have no direction, if we just have magnitude, then we don't have to worry. Then we can think of the angle between A and B to be 0. So if I have, I just had to decide on what colors I want A and B to be. So if I have A, In this case, we would not write this as a vector, but if the magnitude of A is equal to 2, and the magnitude of B is equal to 3, I have to pick two things that I can multiply. Normally, we're not thinking of these as vectors with direction. We're just thinking of this. All right, I make $2 an hour and I work for 3 hours. I multiply those two things and I get $6. I need to think of this as 3 2s. Or I can think of this as 2 3s. Everything's going in the same way. This is the normal way we think about multiplication. If we're both pulling together and I'm pulling with a 2 and you're pulling with a 3, then together we're pulling with a 6. If everything's in the same direction, this is our normal multiplication. Oh, I don't want to say it's normal and abnormal. Let's go with classic multiplication. Call it classic. Multiplication classic. Not new formula multiplication. But now, if I have a vector as that's going off at an angle, compared to my other vector, my product is not just going to be the length of A times the length of B, because they're not completely working together. We're at an angle of some number of degrees, or some number of radians. I have a trig class, so I'm going to refer to lots of things in terms of degrees. On semesters where I don't have trig class, everything kind of slowly converts to radians. But when I have a trig class, I just kind of like convert my mind to degrees. I don't know why. Actually, I know why, because my trig class is not in radians yet. So what we want to do is we want to look at how much of A is in the direction of B, because that's what we're going to be multiplying. So we want to know how much of A is going along with B. Because we want to do our old problem. I just want to take the length of A and the length of B, and I'll multiply those two things. But we're at an angle, and that's why that's where the dot product is going to show up. All we're doing is the same thing that we always do. We break A into components, one parallel to B and one perpendicular to B. We only care about the one parallel to B. And so right triangle trigonometry says that the length of this vector in the direction of B will be the magnitude of A times the cosine of the angle between A and B. So our multiplication at an angle we want to indicate it with something other than just multiplication. So we call it the dot product. Product because we're still doing multiplication. Dot because of the symbol that we're using. This makes our reader notice, we're doing multiplication at an angle. Direction is involved. And I just take how much of A is in the direction of B. And then multiply that by the magnitude of B. This is not how we normally write it. We normally write the cosine of theta at the end, like a rational person, and put the A and the B, our scalars, up in front. Now, the scalar part of the vector up in front. Now, I wrote this from perspective of how much of A is in the direction of B, but it works the same way if we do a projection of B onto A. So if I look at the line on which A sits, I can also make the projection of B onto A. And this length is the same thing because it's still the same theta between A and B. So I'm still going for the adjacent side to theta. So here, this magnitude is the magnitude of B times the cosine of that same theta. At which point we would be reading the magnitude, the A dot B. Here I would take the full magnitude of A and multiply by how much of B is in the direction of A. Any questions? The dot product is just multiplication. This is how we multiply when direction is involved. So A dot B is magnitude of A times the magnitude of B times the cosine of the angle between them. Is everybody okay? It's hard to say because like maybe everybody's thinking like, oh, dude, we were okay with this yesterday, the first time you said it. But like I always say, you don't get a song stuck in your head because you hear it once. You get a song stuck in your head because you hear it thousands of times. And depending on how you listen to music, maybe you get the song even more stuck in your head because you watch someone deconstruct and analyze the whole song lyrically and musically and stuff like that. But that would only apply if you're like a gigantic nerd. Ask me how I know. Any questions? How's everybody okay? Everybody looks so sad. Or maybe it's just tired. I don't know. Why don't we build a society where we're tired all the time? I think we fucked up. There are a lot of people that notice things like how psychologically damaging like hustle culture is. Do we all recognize that this was a really fucking bad idea? It's like, well, hey, all your free time, you could be working. And it's always cast that way. It's always like, hey, in your free time, you could be working. But that's not really the message. What's the message? In your free time, you should be working. That's the message. Your free time should be done doing something. As if that means anything. You know what I mean? I'm just worried about we're not going to let die out this idea that if you're doing something that allows you to relax, I don't want guilt to go along with it. There's a lot of people my age when they're not doing something that's like productive, at the very least making money, but at least productive, cleaning, getting something ready for someone else, whatever, you feel guilty about it. And I think that's one of the things that we need to get rid of. And then of course people come at me and say like, oh, but Leach, some people can't do that. And my response is, thank you for pointing that out. That means the rest of us need to figure out how to make that not happen. That's it. If people can't do that, we need to figure out why not, and then find a way so that they can do that. You know what I mean? All right. That's my message of hope for the day. We can do better. We can take care of each other. And we don't all have to hate existence. All right. So that's our clarification on dot product. This is the clarification I want to make. I really want this idea of dot product being multiplication at an angle, multiplication where direction is involved. And it is just a slight modification. It's just a slight modification of our normal multiplication. It's how much of one factor is going in the direction of the other factor. Those are the ones that we want to multiply. And then we also know how much is missing, right? We can just subtract or just do the magnitude of A times a sign to find out how much is kind of like being not used to move forward. When everything aligns, we get full amounts. no tax of this cosine of an angle, but when our factors are working at angles, we're losing some of not just one of them, but both of them in our final product. Oh. So we've talked about gradients in the plane. We were referring to surfaces at the time, but we were kind of looking at it top down. We know that the gradient of a function of two variables is going to indicate the direction of maximum increase, and that the gradient will be perpendicular to the level curve. So it's that f of xy is a surface. F of xy is a surface in R3. It's got three variables, x, y, and then the output f of xy. So we're in R3. We know that if we put the height above every point in xy, we will get a surface in R3. The gradient will indicate the direction of maximum increase, and this will be perpendicular to the level curve. A surface in R3 will have level curves, one-dimensional level curves. Let's consider a function of three variables. We have a function of three variables. That means there are the function of three variables must be sitting in R4. There are four variables running around, x, y, z, and then the output. So there are four variables. We've gone from a one-dimensional curve in R2 to a two-dimensional surface in R3. This must be a three-dimensional solid in R4. So at each point x, y, z, we go out to the height, and we'll create a three-dimensional solid in R4. So the surface is 2D. We've got a function of three variables. For perspective, we're dealing with a three-dimensional solid in four-dimensional space. Hard to picture because it's in four-dimensional space. I mixed some LSD in my coffee so I could see into 4-dimensional space. Did a little too much. I'm looking into 5-dimensional space. It's a bit of a struggle. I'm just kidding. There's no LSD in my coffee. I put it in my toothpaste. I'm just kidding. That would be disgusting. I'm only on caffeine and ibuprofen. That's not so I can see in 4 dimensions. So I'm just going to pretend to see in 4 dimensions because I don't have to, because we have equations. That's why we have equations in the first place. So we can picture like 4-dimensional things like in the equations and not actually have to draw a picture of it in space. So we've got a 3-dimensional solid in R4. We're going to want to build a gradient. We've got a function of 3 variables. So that means we're going to have 3 directions. I don't even have to tell you how to calculate the gradient. The gradient of a function of 3 variables, we start off with the x derivative in the I direction. Then we do the y derivative in the j direction. Gosh, I wonder what we're going to do. How we're going to take the other one. We do the same thing. If there were more, we would just keep going. Like I said, Calc 3 is the easy one. I love it in math when what you think is going to happen is exactly just what happens. So this is the gradient of a function of 3 variables. We're calling this a gradient. It should have gradient type properties. What are the gradient type properties? It should be the direction of the maximum increase. And so it is. This is going to be the direction of maximum increase. Our gradient was perpendicular to level curves. We don't have level curves so much because we have a 3D solid in R4. What we've got are level surfaces because everything's gone up 1. So it's going to be perpendicular to the level surface. Where before we had level curves, sentences are getting harder to write. Where before we had a surface and had level curves, in a solid, we will have level surfaces. At different surfaces inside the solid, we'll have the same value of the function. So this is going to be a level surface is just a 2D surface in the solid F. If we run tangent to the level surface, we'll be staying at the same value. Now, in this case, our tangent is a whole plane because we're looking at a tangent to a surface, a whole surface where things are the same. If we stay tangent to that surface, all those directions are going to represent no change, just like tangent to the level curve represents no change. So the maximum increase will be perpendicular to the level surface, just like the maximum increase was perpendicular to the level curve. Same thing, but more of it. If we had a function of 4 variables, the thinking would still be the same. Although it gets a little bit weird. We start running out of words for things. A 4-dimensional hypersolid in 5-dimensional space. It's not gonna have level surfaces, it's gonna have level solids. That getting weird. One of the questions that we might be asking is always the same thing with the derivative question. The derivative question is like, well, how much is this changing? How much is our function changing in a particular direction? So if we want the derivative of this function at a point in a particular direction, we do the same thing that we always do. We even use the same notation, there's just more of it. Oh, actually, I'm gonna find that I don't have to write out the gradient. I can just write gradients. We just grab the direction u, want a unit vector for the magnitude of 1 because the dot product is going to multiply our magnitudes. And I'm just going to ask the question, how much of the gradient is going in that direction? And we know that the magnitude of u is equal to 1. The magnitude of the gradient is the maximum amount of change for our function. I want to know how much of that maximum amount of change is going in the direction of u, the unit vector. So I just multiply the gradient, the magnitude of the gradient times the angle between the gradient and the direction we're interested in. Now we're just saying how much of the gradient is going in the direction. I want the whole vector. Understand the dot product so that we don't, as multiplication with direction involved, so that we don't see this as just some weird thing that we do. When we look at the directional derivative, we want to think, of course, this is what we do, because that's how we figure out how much of one vector is going in this weird direction. This will help us remind us that the unit vector needs to be a unit vector, because I don't want to multiply the magnitude of the gradient by some magnitude of a vector. I just want to know how much of that vector is going in a direction. All I want from the unit vector is the direction. I don't want any magnitude from that. How's everybody okay? think that's it. That's what I wanted to do. That's what I want to talk about today. I wanted to clarify the dot product is multiplication with direction involved. And I want to take the gradient that we've been talking about and move it up one dimension. Gradient in plane up to gradient in space. Think about the context in which we're defining our gradient. Think about what we want to think about the gradient. Direction of maximum increase. The magnitude is the maximum increase. And that the direction of the gradient will be perpendicular to the level, whatever. Perpendicular to level parts. That's it for today. I will see y'all on tomorrow. Everybody have a good day. And thanks for playing.